Chapter 14, MRP and ERP. By the end of this chapter, you will understand the difference between dependent and independent demand. You will know how products are structured using a bill of material and how materials requirements planning and enterprise resource planning systems work together to manage complex business processes. Wheeled Coach manufactures ambulances with 12 major designs made up of 18,000 different inventory items. Most parts are purchased, but a large number are manufactured internally. The goal of the material plan is to match the requirements of the master schedule with the production capacity. Cost is controlled by minimizing inventory. These complex systems require excellent record integrity to be successful. In another example, we show a disassembled laptop computer. Notice the variety of components, some purchased and others manufactured. Independent demand does not depend upon other items. For example, customer orders for finished goods are independent demand. Dependent demand occurs when the demand for one item depends upon the demand of another. This is the case for components and subassemblies. In this example, computers are independent demand, while the keyboard and circuit board are dependent demand, based upon the computer's independent demand. Similarly, the memory and microprocessor demand is dependent upon the circuit board demand. This table shows how dependent and independent demand compare. We can see how the source of demand, material type, and demand estimation compare. In previous chapters, we reviewed the use of economic order quantity and reorder point for planning independent demand. For dependent demand, we use materials requirements planning, or MRP. Here's a view of all the components of a Volkswagen Jetta. The bill of material is a structured breakdown of all the subassemblies and components within the vehicle. Dependent demand is when the demand of one item is related to the demand of another. For example, if 4 tires are used on a car, for every unit of independent demand for one vehicle, there is a dependent demand of 4 tires. If 100 cars are ordered, dependent demand for tires would be 400 tires. MRP is typically used to manage dependent demand flexibly while maintaining minimal inventory levels and thus lower cost. To effectively manage dependent demand, we start with a master production schedule for the independent items. Next, an accurate bill of material is used to expand the demand of the subassemblies and components. To complete the planning process, an accurate inventory of material on hand, along with outstanding purchase orders and supplier lead times, are needed. The master production schedule is the top-level plan of finished goods to be produced. While based upon the demand forecast, the two may vary. The production schedule must consider production capacity limitations along with available inventory and staffing. This graphic compares 3 common process strategies. With the 3 methods, raw materials start at the bottom with finished goods at the top. Make to order waits until the customer order is received, then the manufacturing process starts. Think of Starbucks. The materials are available, but your drink is not created until after your order is placed. Assemble to order operations have subassemblies manufactured to forecast with final assembly once the customer order is received. This is the case for automobile and motorcycle assembly. Finally, stock to forecast builds to plan and stocks finished goods available for customer purchase. Think of most of the items available at your local grocery store. One key difference is the point of scheduling. For make to order, there is limited forecasting since the work is not done until the order is received. Conversely, forecasting is critical for stock to forecast. This diagram shows the planning process. Inputs include production capacity and inventory, customer demand, and cash flow. Other inputs include procurement and supplier performance and staffing. Based upon these inputs, an aggregate plan is created which feeds the master production schedule. This schedule defines the manufacture of specific products. The materials requirements plan is created from this schedule to identify the detailed build requirements for subassemblies and components. The plan also verifies whether the master production schedule is realistic. The master production schedule may need to be adjusted. Finally, once the material requirements plan is finalized, schedules and execution plans for the production work centers are created and published. Here we see the material requirements planning structure. Inputs on the left include bill of material or BOM data, lead times, inventory, and purchasing data. Given this data, the MRP software algorithms generate the plan by period and by date. Factory orders and supplier component orders are generated with appropriate quantities and due dates. Finally, exception reports identify any issues that require management attention. Here's an example showing an aggregate plan and how it relates to the master production schedule. The aggregate plan calls for a total of 1,500 amplifiers in January and 1,200 needed in February. The master production schedule takes the aggregate plan and breaks it down into specific products and weeks. For January in week 1, we are building a quantity of 100 240 watt amplifiers. In week 2, we are building 500 150 watt amplifiers. Then in week 3, 100 240 watt amplifiers and 375 watt amplifiers. Finally, in week 4, we build 500 150 watt amplifiers for a total of 1,500 amplifiers. We continue this process until every month of the aggregate plan is covered. Bills of material, or BOMs, are lists of components and materials needed to make a product. The list is hierarchical in that multiple levels exist to include the components of subassemblies. Items above a level are called parents, while those below are called children or components. This diagram shows the structure of a BOM for the Awesome A product. A is the parent of subassemblies B and C, while B is the parent of D and E. C is the parent of E and subassembly F, while F is the parent of D and G. Note that some components, E and D, are used in multiple subassemblies. The numbers in parentheses indicate the quantity used. For example, 2 Bs are used to build every A. This level shows how far down in the tree structure an item exists. The final product is at level 0. We add detail to the BOM diagram identifying each item. We are reminded that Awesome A at level 0 is driven by independent demand, while all lower levels, 1, 2, and 3, have demand that is dependent upon the demand for product A. Given an independent demand of 50 units for product A, we want to determine how many subassemblies and components need to be manufactured or procured. We start with the assumption that there is no existing inventory at any level. As noted, since there is a 2 in parentheses next to subassembly B, there are 2 Bs required for every A required. To calculate the dependent demand for subassembly B, we take the independent demand of A, which is for 50 units, and multiply by 2 to get B's demand of 100 units. Since we need 100 B's, we find that we need 2 times B's demand, which equals 200 units for item D. We perform the same calculation on down the BOM structure. Note that since items E and D are used in multiple assemblies, the gross demand is found by adding demand in each case. Here's a summary of the dependent demand for the items that make up the BOM structure for Awesome A. Again, we notice that parts D and E are used in 2 assemblies. We combine those demands. So to fulfill an order of 50 A's, we will need a total of 800 D's. In the previous example, we started with no inventory and created only what we needed, so there was no ending inventory. Now let's include inventory in our analysis. We start with some on-hand inventory and have ending inventory left over after the full order has been shipped. We start with a total requirement to create our demand along with an amount of ending inventory. We start with the existing inventory added to the amount we expect to produce. Returning to our previous BOM structure, but adding that we have a starting inventory, we redo our calculations. For item A, we have a demand of 50 units, but an existing inventory of 10 units, so our net demand is 40 units. For item B, we need 80 units since 2 are needed for each of the 40 A's required. But then we subtract the existing inventory of B's, 15 units, for a net demand for B's of 65. As before, we step through the BOM structure to complete the calculations. Be careful not to double count the available inventory for common items D and E. Now we know that we need to produce. We must consider the lead time for each item in our BOM structure. For manufactured goods, lead time is the total of setup and manufacturing along with any product movement. For purchased items, the lead time is the time from order placement to delivery of goods. The lead time for each component is listed here. This diagram shows how the component lead times stack up across the BOM structure. For example, items D and E must be available to build item B. Looking at the total time, it takes 4 weeks to build product B. Looking at the total BOM structure, a total of 8 weeks is required to complete the final assembly, product A. Your MRP software takes all the individual lead times and builds a schedule to create or procure all the individual items and subassemblies based on the independent demand for the end product. This is a step-by-step summary of the process of determining gross requirements for each component and subassembly. The process works one level at a time so that items with multiple parents are processed only once. At the end of the process, the quantities and timing for each is fully defined to be communicated with manufacturing managers for manufactured items and procurement managers for purchased items. This table displays the outcome of this process, showing weekly demand and due dates for the quantities of each item. Notice how we start with the furthest out items, finishing with final assembly in week 8. Now we factor in the starting inventory previously discussed. Our starting point is shown in the upper right corner. Each block of data represents one item. Item A, the final assembly, starts at the top. Here we see the weekly inventory and order release of 40 additional units. The order release in week 7 creates dependent demand of 80 units for item B. Again, the process looks at available inventory and defines a planned order release for 65 units in week 5. This process continues down the BOM structure until all planned orders have been released. Here we see the continuation of the process through the remaining items. We end with placing an order week 1 with a supplier for item G for 195 units. Our material requirements plan is fully defined. Now we have a step-by-step summary of the process of determining net requirements for each component and subassembly. Net requirements take gross requirements and then factor in starting and ending inventory. These numerous calculations are handled by the MRP software to ensure speed and accuracy. Here's an example for multiple products with shared components. Item B has dependent demand as part of products A and S, plus there's also independent demand for product B. At the bottom we see the weekly requirements for product B combining the demand for all 3 uses. The arrows show how the data is connected. Again, this is another advantage of using an automated MRP to address this complexity. Due to variability throughout the process, we add safety stock. Safety stock addresses inaccurate forecasts, quality issues, delays, and shrinkage. Like in the inventory, there is cost involved, so we want to manage safety stock carefully. Operating an MRP system requires care. If planning occurred once, the process would be very straightforward. Unfortunately, change occurs. Frequent changes can cause instability and create system nervousness. Plus, if the production floor sees a continuous stream of changes, they may spend too much time reacting to change rather than producing product. To control this problem, time fences and pegging are added. Time fences simply state that no planning changes are allowed within so many weeks of production. Pegging ties items directly to their parent items to increase stability of planned requirements. MRP systems are planning systems and work best in repetitive environments. Different methods are used to determine the optimal lot size. The economic order quantity, or EOQ, requires a constant demand, which is unlikely. Periodic order quantity, or POQ, orders variable quantities at a fixed interval. Finally, the Wagner-Witten simulation model is used for a more dynamic approach. The calculated lot sizes may not be feasible due to supplier lot size restrictions. Here we see a lot-for-lot example. Lot for lot simply places demand upon suppliers that exactly matches current demand. The assumption is that with 1 week lead time, the supplier can provide any quantity requested. The week number is shown across the top of the table, followed by the gross requirements. There are no inbound orders in place, so the next row is blank. The third row shows the inventory carried over from week to week. Since our orders exactly match our demand, there is no carryover after the first week. Net requirements show the gross requirements minus the inventory on hand. The planned order receipts line shows the quantities of vendor supplied material due each week. Since the lead time is 1 week, the planned order releases occur 1 week prior to the expected receipts. Now we consider the economic order quantity. Based on the EOQ equation and given the holding cost, setup cost, lead time, and average gross requirements, we get an EOQ of 73 units. Orders for 73 units are placed during weeks 1, 4, 6, and 9 based upon the net requirements. For the period order quantity, or POQ, we vary the orders and order on a regular basis. The POQ interval is calculated to be roughly 3 weeks. Since it is not exact, we end up with an interval of 2 or 3 weeks based upon the net requirements. Looking at the 3 different plans, we can calculate the setup cost as the number of orders multiplied by the individual setup cost at $100. With the same holding cost of $1 per week per unit, we can calculate the cost based upon the product on-hand inventory. The total cost is simply the sum of setup and holding cost. In this case, we see that the POQ model is our lowest cost approach. Note that the Wagner-Witten simulation would yield a total cost of $455, beating the other alternatives. In addition to the features discussed, MRP has been extended to MRP2, closed-loop MRP, and capacity planning. MRP2 is often called material resource planning. This enhanced version can identify scrap, packaging waste, effluent, and carbon emissions. The tool encompasses the purchasing, production, scheduling, capacity planning, inventory, and warehouse management functions. Here we see the output of MRP2, or material resource planning. Note the added detail regarding labor, machine hours, emissions, scrap, and payables. The extra data takes the analysis to a new level. With closed-loop MRP systems, we start with the aggregate plan, which is used to develop the master production schedule. The schedule considers the overall resource availability to see if the proposed master production schedule can be met. If not, the information is fed back to the aggregate plan, which must be modified to fit. Once there is alignment, we pass the master production schedule down to prepare the materials requirements plan. Here again we check for available capacity to see if the MRP is reasonable. If not, feedback is provided to the master production schedule to request a change so that there is alignment. Once alignment is achieved, the detailed production activity control is defined, and execution of the activity begins. Capacity planning is the task of aligning the requirements with the available resources. Data from the MRP is used to define the specific resource requirements for each work center. Work may be moved in time or between work centers to bring the load within available capacity. There are different methods used to smooth the workload to match capacity levels. Overlapping is when a partial lot is sent to the next workstation so that they may get a head start. Splitting sends the lot to 2 or more work centers working in parallel. This action will reduce time, although this will incur multiple setup costs. Finally, order splitting breaks up an order into smaller lots to get a head start. These charts show the impact of order splitting. On the left, we find that we have excess capacity during weeks 1 and 4 and insufficient capacity weeks 2, 3, and 5. By splitting orders and adjusting the schedule, in the second graph, we see we are still over capacity, but this can be resolved with small amount of overtime. We are much closer to the goal of level loading. Let's shift gears and consider services. MRP solutions will work in services since delivery of certain services is dependent upon the completion of others. Thus, the demand for one is dependent upon the other. For example, in a restaurant, cooking is dependent upon the order-taking process. We see similar cases with several different service operations where one activity must be completed prior to the other. Here's an example of an MRP service structure, the equivalent of a product bill of material. Notice that the final meal has two components. We can see the different structural levels as we go from completed meal down to purchase components. Using that same meal structure, we can create a formal bill of material, listing the specific ingredients and their associated quantity, measure, cost, and included labor. Once we have an estimate of the independent demand for the buffalo chicken mac and cheese, we can use this structure for inventory management and cost estimating. Since we have a labor estimate as well, this data is the start of a capacity plan. Distribution resource planning, or DRP, is used to manage product distribution. The gross requirements for distribution come from the independent demand requirements. The goal is to follow the flow of material through the supply chain from suppliers to the ultimate customers. Small and frequent replenishment is the goal. Enterprise resource planning, enterprise resource planning, or ERP, expands the MRP system to include customers and suppliers. ERP uses automation to integrate business processes across the supply chain, extending beyond the walls of the primary organization. To be effective, suppliers must share common processes, data models, and databases in real time. ERP starts with MRP and adds finance, human resources, supply chain management, or SCM, customer relationship management, or CRM, and sustainability. Sustainability includes management of waste, carbon footprint, and other environmental factors. This flowchart shows the major modules of ERP and the high-level data flow. Note the variety of databases embedded within each module, along with the data flow between them. Note that CRM includes both ends of the process, ordering and invoicing. Finance handles the primary functions of accounts receivable, accounts payable, payroll, and general ledger. The advantage of enterprise resource planning is the opportunity to manage the operation, streamlining the activities, and reducing costs. Data duplication is eliminated, and all data is in alignment. This capability facilitates advanced production methods like just-in-time. The downside is that these systems are very large, complex, and costly to implement. They also require regular updates and force the operation to tailor their processes to align with the ERP system. The company SAP provides a commonly used business ERP tool. This diagram shows the major modules within SAP along with the primary functions of each. Oracle also provides an ERP solution. Specific custom ERP templates have been developed for several service sectors. Healthcare services and governmental agencies are among the templates that have been created. The goal is to link all elements of the business together to share data, drive common processes, and optimize the customer experience.